you've got the Higgs, which to our knowledge, it is purported that the Higgs is the one known elementary scalar field that is everywhere. Now, you can have different fields and stuff like that according to quantum field theory. And the whole concept is you got this field interacting with this field is doing this, but basically everything with mass is essentially resonating, or at least from what I remember from, I believe, Dr. Matt Strassler's Waves in an Impossible Sea, which I listened to the audiobook going cross country. And I think he did a really good job because he's like, I'm not going to claim particle, I'm not going to claim wave. So he's like, I'm just going to call it wavelengths, whatever those may or may not be. So I think he did a pretty good job, and at least other science communicators have recommended his book. So I'm like, let me learn. But the idea is that if the Higgs field is here and everything is kind of like oscillating or has some interaction and reference to the Higgs, because if those other fields exist, and again, I'm not a quantum mechanic or a field theorist technically, if you have those interactions, those other fields, well, if you don't have a top quark, or basically if there's no other stuff there, that field may have a value of 0. The Higgs field is unique because it is the one field that has a non-zero value. Okay, or vacuum expectation. I won't take this. The whole concept is you got the Higgs mass. All right, so Higgs. And now the Higgs has different characteristics, but the big thing that we usually measure things is mass. All right, so mass. All right. But we want mass energy because we want energy density. That's how we're working through this. So we literally do, thank you, Professor Einstein, E equals mc squared. Our mass, the speed of light squared. Terrible. Okay, it's a little better. Okay, so now the whole concept is, and again, a lot of this was just, I was just kind of curious because I'm like, there's a lot of smart folks, far smarter than me, working on this, and I would see papers and they're going in trying to solve all this inflation and everything. It's like, listen, that's really hard. I'm not that smart a guy. But I remember Professor Carroll had one of his, I think he was explaining, it was one of his solo explainer videos, I believe. But at one point, he literally was talking about, the hierarchy problem and stuff. And he was talking about, it's kind of like the cosmological constant problem. It seems to be, why does it have this value it has? It seems very weird. And the term you'll hear is unnatural. What does that even mean? Number one, that's a human preference. And nature is under no obligation to be like, you know what? We're going to do this because it makes sense to you. Maybe that's the case. Maybe we're literally just missing it. But I'm like, okay, so if we have an energy now, so we have a mass energy, we need to divide it by a volume. So we'll get energy density, which another term for that is pressure. Under pressure. Basically like that. So also what I had learned from Professor Carroll, to bring it back to the spherical cow, is in episode 1 of The Biggest Ideas in the Universe, he introduces a concept called the spherical cow, which in physics, what are we assuming? We're assuming an idealized scenario that doesn't actually exist, because I don't know about you, but I've never actually seen a spherical cow. We are assuming optimal conditions. We know that doesn't exist, but at least if we try to isolate as many factors as we can get a better idea what might actually be going on, and then we can add additional factors and interactions and complexity and go from there. Okay. So what I'm like, all right, I got this. Let's turn it into a spherical cow. How? Well, we live in what appears to be three dimensions of space. It's like, all right, well, let's divide it by 4/3 pi, and r cubed. What is this r? It's the Higgs. There's a little symbol thing, Compton wavelength. Higgs. Okay. Because there's also a thing called the Compton wavelength. Professor Carroll has also been harping upon more recently, in that, what's the heck? It's the Compton wavelength. basically you take Planck's constant, you divide it by mass, and then one of these speed of lights. Okay. It will give you out a length because the dimensions will cancel out. Okay. So we're using Planck's constant of proportionality. Now, again, you could use the reduced Planck's constant, and again, factor of 2 pi or something here. I like this one just because it came out to be right about a whole number with Wolfram Alpha's estimation. So it's kind of got that shock value. But the whole crazy claim is this is going to give you a really big number. Why? It's because, all right, this is a mass and particle physics that's decent size. This is a really small wavelength. Gives you a ridiculous factor, but when you divide it into the vacuum energy density of our realm, so basically the whole vacuum that's not a true vacuum because there appear to be quantum fluctuations and stuff going on, basically that's about 3.5 giga-electron volts per cubic meter. Okay. So this number is a lot bigger than that when you divide it into the vacuum energy density. It's like, so you take, what is it, rho lambda, or something, yeah. So, what show are we doing? No, we're doing, so it's that kind of like sideways-ish P, funky looking P, yeah, the lambda, that's an A. So basically, when you take that, you divide it by the cow, you get basically 1.1. And again, this is, excuse me, it's not equal. It's approximately, we want to be honest here, times 10 to the minus 52. And it's a dimensionless number because this is an energy density divided by an energy density. Now, the cosmological constant has dimensions. But cosmological constant is basically 1.1 times 10 to the minus 52 reciprocal meters. So basically that's 1 over meter squared. Okay. I was not expecting that, but I'm like, all right, that's kind of cool. And then when you take Einstein's kappa constant, so you get like little k there, and then you multiply it by the cow. You basically get out, again, approximately 1 reciprocal meter squared. So wait, that's the dimension that we and again, that vacuum energy density, some folks may say, oh, is this the dark energy? But basically, you get out the reference unit when you multiply it, and then you get out the magnitude just as a dimensionless relationship. I think that's kind of cool. Now, full disclosure, if you put in any mass and then you multiply this number by that number, the numbers will change, but ultimately, if you're dividing by a cow and multiplying by a cow, it's just going to net out to nothing. It's just going to net out to 1. So those have a direct relationship. So combined, the interesting thing was the Higgs under this formulation kicked out the dimensionless number that matched the cosmological constant, again, based upon our observations, assuming that, and again, who knows, maybe it's an observational thing. Who knows what's actually going on, but this also popped out the reference unit for it at approximately a magnitude of 1. So